Welcome to the deep dive. If you're stuck in traffic, commuting on the train, or just trying to catch up on the future of digital worlds, you are in exactly the right place.
That's right.
Have you ever stopped to think about how fast the virtual environments you play in are being created? I mean, it's not just about better graphics anymore.
Not at all. It's a fundamental reinvention of the process, from the initial art concept all the way to the final frame that hits your eye.
It feels like everything is accelerating.
It is an incredible period of acceleration. The 2026 development roadmap is really being defined by two major interconnected forces. Radical automation through generative AI and pushing performance to, entirely new, previously unimaginable levels.
Right.
We're deep diving into a world where assets are invented by machines, code is written by algorithms, and games are delivered instantly right over the cloud.
So our mission today is pretty simple, but it's ambitious. We want to give you the complete current mental map of the modern development ecosystem. We've processed a massive stack of sources on this, covering everything from the generative AI tools that can make a high-fidelity 3D model in seconds to the philosophical and technical battle between programming languages and the cutting-edge cloud magic that removes the need for downloads entirely.
This deep dive will really illuminate where the real innovation is and, frankly, where the venture capital investment is truly flowing.
Yeah.
You are going to walk away with a clear understanding of the speed at which AI is working right now and just how close we are to technologies like 8K resolution at 120 frames per second becoming the expected standard rather than, some developer's dream.
I'll be your guide through the big, exciting trends, and I'll be posing the questions that lead to those aha moments that change how we think about digital creativity.
And I'll be breaking down the technical battles, providing the crucial context, why developers choose C++ over C#, how hybrid AI systems are making NPCs genuinely smart, and the practical implications of the upscaling showdown between DLSS and FSR.
Okay, let's unpack this. Prepare for some mind-blowing facts as we start with segment 1. The new creator class AI generating 3D worlds. It really seems like only yesterday we were all fascinated by tools like Midjourney creating these stunning conceptual images. It was amazing, but it was flat.
Right, it was all 2D.
Now, generative AI has decisively moved beyond simple 2D images and textures into creating high-fidelity, production-ready 3D models. This feels like a massive fundamental change to the initial development pipeline.
Oh, it changes the concept of production lifecycle completely.
Yeah.
I mean, traditionally, if an artist needed a new prop, say a specific medieval-style torch or a unique environmental rock formation, they would spend days or even weeks modeling, unwrapping, and texturing that asset by hand.
A ton of manual work.
A ton. Now, a developer or an artist can just type a prompt, like a rusty, slightly futuristic vending machine, and receive a full, optimized, textured 3D model in under a minute.
In under a minute. That speed alone has to have colossal financial implications.
It does. Our sources ran a direct comparison, ranking the top 3D generators of 2025, and it really distilled down to a classic tech industry trade-off: speed and value versus absolute premium quality.
Okay, so let's break down that ranking.
That's right. Leading the charge in speed and overall value is a tool called Magic 3D. It earned the best overall ranking.
Magic 3D?
And the key feature here is just astonishing generation speed. The sources showed it averaging just 20 to 30 seconds per model.
Wait. 20 to 30 seconds, not minutes.
Seconds. And to give you some context, that means Magic 3D is about twice as fast as its main competitors in the general purpose category.
That's insane.
And critically, it delivers this speed and reliability at a cost that is significantly lower. We're talking 50 to 100% cheaper than other viable alternatives.
So for an indie team, or even a mid-sized studio?
It's a no-brainer. It makes it the clear choice for indie teams, hobbyists, and any mid-sized studio that's prioritizing rapid iteration and budget control.
But if you're making the next big blockbuster movie or a massive AAA game where budget is maybe secondary to photorealism, you might look at the other champion.
Exactly. You'd look at Rodan AI, specifically their Hyper 3D tool.
Rodan AI, backed by ByteDance.
The very same. Rodan AI, with that significant research investment, scored the highest quality ranking at a monumental 9.5 out of 10. They are focused entirely on premium output. What the sources are calling film quality assets and photorealistic textures, they are the absolute premium option.
And this is where that surprising trade-off really becomes clear, because Rodin delivers that absolute best quality, but it comes at a significant time and cost premium.
A huge premium. Rodin takes significantly longer, anywhere from 60 to 120 seconds, sometimes 85 seconds on average, so double or triple the time.
On the price.
The pricing curve is steep. Magic 3D offers excellent value, with starter plans available around, say, $9.99 a month. If you want Rodin's premium features, their Pro tier, which gives you about 300 creation credits, will run you $79.99 a month.
Wow.
So the conclusion of the sources was really sharp. Magic 3D provides 95% of the quality delivered by Rodin, but at roughly a quarter of the financial cost and twice the speed.
For most developers, that value proposition is simply unbeatable.
It's unbeatable.
And when we talk about production readiness, it's not just about how good it looks. The output format is just as important as the quality. An asset is useless if your engine can't actually read it.
Absolutely. We need to stress the practicality for the listener here. Magic 3D really stood out for supporting a wide range of production formats, including GOB, STL, which is great if you plan to 3D print your assets, OBJ, and most critically, FBX.
Okay, so what exactly is FBX and why is that one so essential for game development?
FBX stands for Film Box Format. Think of it as the universal interchange standard for 3D data in the industry. It's like the PDF for 3D models.
I like that.
It can hold not just the model's geometry and textures, but also critical things like animation data, rigging, and camera information. Without robust FBX support, the models are hard to integrate seamlessly into major engines like Unity or Unreal. These tools are only revolutionary if they create assets that can be immediately dropped into the development workflow.
And this capability, this generative power, is causing an economic boom. The scale of investment is just staggering.
It really is. The global generative AI market is forecasted to grow from $13.5 billion in 2023 to over $43 billion by 2025.
$43 billion in just 2 years.
That is one of the fastest technology adoption curves we have ever tracked. And it signals one clear thing to venture capital and major studios. They're prioritizing automation over human asset creation.
That's a huge bet.
They're making a massive bet that the majority of digital content will soon be created by algorithms, leaving human designers to focus on high-level concept, refinement, and quality assurance rather than, the repetitive modeling tasks.
So this isn't just for models, right? AI is also being used to generate actual code.
Oh, absolutely. That's another huge part of this. Generative AI is used to generate code, and some sources suggest it can reduce development time by up to 70%.
70%.
It's a massive productivity boost.
And while this 3D generation is exploding, the original visual tools, the 2D ones, they're still crucial for conceptualizing.
They still hold highly specialized roles. Midjourney remains the reigning champion for creating stylized, painterly, or surreal conceptual art. If you need a mood board, a unique initial sketch, or an artistic vision that breaks reality, Midjourney is still the go-to.
And DAE3 occupies the niche of accuracy and commercial integration.
DAE3 is known for its highly accurate prompt understanding and delivering exceptionally high-resolution commercial outputs, especially because it integrates so seamlessly into existing tools like the Microsoft Designer ecosystem and the ChatGPT interface. It's perfect when you need a very specific result based on a really complex textual instruction.
So the modern pipeline starts with Midjourney, or DAE, creating the conceptual art, which then guides a few clicks that generate production-ready 3D assets via tools like Magic 3D. Those FBX files are then ready to be dropped straight into the next major step, the engine. All right, so once those hyper-fast AI-generated assets are built, they need a robust environment to live in, right? An engine that can handle the sheer volume of data and render it quickly. That takes us under the hood into segment 2, the engine and language wars.
This section really addresses the core tension in high-performance digital creation. The perennial conflict between raw performance and developer productivity.
Okay.
And that conflict is perfectly embodied by the C++ versus C# debate.
Let's use an analogy to simplify this complex distinction for the listener. I know this can get pretty technical.
Let's do it. Think of it this way. C++ is the high-performance stick-shift race car. It's built for maximum speed, but only a master mechanic should be driving it. Its ultimate superpower is manual memory management. This means the developer is responsible for allocating and deallocating every single piece of memory the program uses.
Why is that a superpower, and what's the risk involved there?
It's a superpower because that total control allows developers to optimize the frame rate budget down to the millisecond. They can ensure that memory allocation happens at the most efficient point in the frame. If you need unparalleled versatility and raw processing capability, For, say, an intense physics simulation or complex AI systems, -C++ is the undeniable, indispensable choice.
And the wrist.
The risk. If you forget to deallocate memory, you get what's called a memory leak, which ultimately slows down, or worse, clashes the game.
Okay, that makes sense. Now contrast that with C#.
C# is the productivity king, and it's the dominant language within the massive Unity ecosystem. So C++ is the stick shift, C# is the luxury automatic car with self-driving capability. Its main advantage is automatic memory management, commonly called garbage collection, or GC.
So the developer doesn't have to worry about memory leaks at all.
Precisely. The system handles the cleanup automatically. This is much safer, it dramatically reduces common bugs, and it allows for rapid development speed and faster iteration, especially for mobile, AR, VR, and indie projects, where that time to market is crucial.
And it's incredibly popular because of that.
It's so dominant in terms of mainstream enterprise adoption that it saw the largest growth in popularity over the last year, earning it the Programming Language of the Year title, according to TIOB index data.
Now, I want to clarify that TIOBE point because it can sound contradictory. Our sources show C++ is still ranked higher overall, sitting at second, while C# is fifth. Can you break down what C#'s Language of the Year title really signifies for developers?
Yeah, that's an essential distinction. C++ remains the foundational pillar globally, particularly for systems programming and, of course, for building the core game engines themselves. But that Language of the Year metric, it measures the largest positive shift in popularity over the prior 12 months.
So it's about momentum.
It's all about momentum. C#'s win is an indicator of its explosive utility and increasing demand in the Unity, mobile, and broader .NET world. The core split remains clear. If you're building the engine or a high-performance AAA core, you choose C++ way. If you're building a vast ecosystem of apps and rapid, iterative projects, C# is your language.
Okay, beyond the big two, we have two other key languages that are critical for modern game development, starting with the undisputed leader in tooling, Python.
Python.
It's ranked third globally on the TIOBE index, and it completely dominates AI, machine learning, and data science. It's highly readable, meaning the code is almost like plain English.
Which makes it great for beginners.
Exactly. It makes it excellent for scripting, for tool development like building-level editors or asset pipelines, and it's the most common entry point for new programmers via libraries like Pygame. Even Godot's language, GDScript, is heavily Python-inspired.
And what about the language that promises to solve the core problem of C++ way, the one that everyone in development seems to be so excited about? That is Rust, the rising star. Rust is the technical darling right now because it promises the performance speed of C++ so deep into that millisecond optimization zone, but it guarantees memory safety at compile time.
That sounds like a game changer. How does it manage to guarantee safety without relying on that automatic garbage collection that C# has?
It's really clever. It uses a complex system of ownership and borrowing rules that are enforced by the compiler before the program ever runs.
So it catches the error before you can even make it.
The compiler essentially checks for the types of memory-related errors like buffer overflows or memory leaks that plague C++ applications, and it simply refuses to compile the code until those errors are fixed. It forces the developer to write safe code from the very start.
So that makes Rust ideal for, what, new engines?
Exactly. It's ideal for new engine development, security-critical systems, and anything that demands both speed and rock-solid reliability.
Okay, that's the code. Now, the home for that code, the engine ecosystem. It's primarily a three-way battle: Unreal, Unity, and Godot.
Let's start with a high-fidelity powerhouse, Unreal Engine 5.45.5. If your goal is photorealism, cinematic quality, and pushing the graphical envelope to the absolute maximum, Unreal is the answer.
And it's all C++, right?
It's tightly coupled with C++ for that deep optimization, and it leverages two transformative technologies.
Those would be Nanite and Lumen.
Precisely. Nanite handles complex geometry. It basically virtualizes billions of polygons, so you can import film-quality assets directly into the engine without a noticeable performance loss. And Lumen provides real-time global illumination, meaning light bounces naturally and realistically off surfaces without needing hours and hours of pre-computation.
So Unreal is the choice for massive, high-budget AAA production and visual showcases.
Undeniably. Then we have Unity 6, the iteration champion.
The C# engine.
Right. Unity 6 maintains its strong lead in mobile, 2D, VR, and AR. Where Unreal focuses on maximum graphical fidelity, Unity focuses on platform accessibility and sheer development speed. Key to Unity's future is the DOTS, or Data-Oriented Technology Stack, architecture.
What does DOTS do for a developer? What's the pitch?
It's a complete philosophical shift in how the engine handles data. Instead of traditional object-oriented programming, DOTS focuses on organizing data for maximum efficiency. This architecture is designed specifically to maximize multi-core processor performance.
Why does that matter so much now?
It makes Unity incredibly efficient when handling thousands of entities, think massive swarms of enemies, complex particle systems, or very detailed physics interactions in projects like demanding mobile games or large VR environments.
So if you are making a game that requires thousands of things moving on screen simultaneously, DOTS gives Unity a real performance edge, even though the engine itself is typically associated more with C# speed.
Exactly. It leverages modern hardware better for entity management. And finally, we have the lightweight rebel, Godot.
Godot 4.x, the open source engine that some people dismiss as a toy, but it's clearly gaining some serious momentum.
Godot is a fascinating case study. It's open source, entirely free, no royalties ever, and built on this extremely clean philosophy that everything is a node, which really simplifies scene construction and debugging.
But it's not really for AAA.
Right. No, it lacks the high-fidelity rendering power of Unreal, but it is noted for its minimal hardware requirements. The saying that it can run on a potato fast is very, very true.
And what are the implications of those minimal hardware requirements? Who is that for?
It makes Godot an outstanding choice for developers in emerging markets, for students who can't afford top-tier hardware, and of course for game jams and small-scale indie projects where development speed and zero upfront costs are absolutely paramount.
Do you have any numbers on that?
We do. The sources confirm this success, showing Godot achieved an 8.2% usage rate among independent developers. That demonstrates its significant appeal in, the democratization of game creation.
We've established the digital factory. AI builds the assets, the engine provides the framework. But what truly makes a game world feel real isn't just the texture on the wall or the efficiency of the rendering, it's the intelligence of the characters and the fidelity of the world's reactions. This is segment 3. Making worlds feel real.
This takes us beyond just basic pathfinding and into the complex world of non-player character or NPC logic. We need NPCs to feel intentional, to make real choices, rather than just following simple, repetitive scripts.
That's the essence of game AI planning. So what are the 3 core frameworks that developers have traditionally used to make NPCs think?
Game AI planning essentially gives the NPC an internal evaluation system to weigh trade-offs and pursue goals. The first, and maybe the most intuitive, is behavior trees, BTs.
BTs are like a high-level flowchart of decisions, right? They're pretty easy to visualize.
They are. They have very clear hierarchical structure, selector nodes, sequence nodes, leaf nodes, which is very easy for developers to read and to debug. This high visibility is great for small-scale, simple decision-making, but they are static. The source material emphasizes a major downside here. If a designer wants to add a new complex behavior, say changing a common enemy from just attack to retreat only when health is below 30% and nearby allies are also retreating, you often have to reorganize and potentially rebuild large portions of the entire tree structure.
So they don't scale well.
They don't scale well at all. They're fragile.
That sounds incredibly fragile for something like an open-world game where complexity is just guaranteed. What's the dynamic alternative?
That brings us to goal-oriented action planning, or GOAP. This is dynamic and goal-driven. The agent identifies a high-level goal. I need to defend this base. And then it dynamically chains actions together, like find ammo, go to cover fire weapon, to satisfy the necessary world state.
So GOAP is highly scalable because if I add a new action like deploy smoke grenade, the system just integrates it if it helps achieve the current goal.
Exactly. You simply define the action's preconditions and its effects, and the GOAP planner figures out if it fits into the optimal sequence. This gives it incredibly high scalability.
But what's the downside?
The major downside is low intuitiveness. It's often very difficult for a human developer or a designer to predict or debug the agent's plan flow. If an NPC starts acting strangely, tracing the cause through a dynamic chain of actions is like searching for a needle in a digital haystack.
Okay, and the third system operates on pure context-dependent math, the utility system.
The utility system, or utility AI, shifts the focus entirely to scoring. Every possible action available to the NPC is assigned a numerical score based on the current context, considering factors like health, distance to the enemy, available resources, and time constraints.
And an NPC just does the highest scoring action.
It simply chooses the action with the absolute highest score at that precise millisecond.
Like the example we found. If an NPC needs to eat, they might score cook from fridge at 0.8 versus order delivery at 0.6. They go with the most valuable option in that moment.
Right. It offers great flexibility and allows for nuanced, contextually appropriate behavior. But the computational cost can grow exponentially with the number of variables you introduce. Every variable adds complexity to the scoring functions, making it a heavy lift for the CPU if you have dozens of factors influencing hundreds of agents simultaneously.
So we have the intuition of behavior trees, the scalability of GOP, and the flexibility of utility AI. The future naturally is combining them.
The future is the goal-oriented behavior tree, or GOBT. This hybrid framework is becoming absolutely crucial. It integrates the dynamic GOAP planning and the utility scoring mechanisms within the intuitive hierarchical structure of a behavior tree.
How does that work in practice?
It essentially uses a new, powerful planning node to handle the complex, contextually optimal decision-making, while the rest of the BT structure manages simple moment-to-moment decisions and maintains that developer readability. It balances all three strengths for flexible, contextually optimal decisions that are still debuggable.
Now that our NPCs are making these highly complex, dynamic decisions, we need them to talk in a way that matches that intelligence. This is the revolution of conversational fidelity, spearheaded by NVIDIA ACE.
NVIDIA ACE, or Avatar Cloud Engine, is an end-to-end suite of AI technologies designed specifically to create knowledgeable, actionable, and conversational characters. This is the absolute end of the static, pre-recorded dialogue tree where you click A, B, or C.
So what are the immediate real-world applications of this technology right now? What can it do?
The applications are stunningly diverse. We've seen AI advisors like those implemented in Total War, Pharaoh, where an on-device small language model can guide the player through complex game mechanics using natural language. We have AI-driven allies, like Kerafton's co-player characters in PUBG, who can communicate tactically using voice and text that feels completely unscripted.
And for adversaries, this must add a whole new layer of difficulty.
Oh, absolutely. We made Next MIR5 uses ACE to power AI bosses that continuously learn from player tactics across multiple runs.
Wait, really?
Yeah. Imagine a boss fight where the AI remembers your preferred strategy and proactively counters it the next time you face them. But the most futuristic use case is in games like Dead Meat, a murder mystery, where the player can literally ask the suspect absolutely anything using natural language, and the character will generate a contextually appropriate, unique response.
That's incredible. But the technical challenge here is running these massive language models alongside high-fidelity graphics. How does NVIDIA achieve that without tanking the frame rate?
That is the magic of optimization using NVGI, or NVIDIA in-game inferencing plugins. Let's clarify inference simply. It's the process of running a trained AI model to generate a prediction, or in this case, a response.
Okay.
NVGI schedules this intensive AI calculation, the inference across the GPU, alongside the complex graphics workload. It ensures that asking an NPC a complex question doesn't interfere with your rendering performance. It maximizes the use of the powerful GPU hardware for both tasks at the same time.
Okay, let's get physical. We've talked about AI thinking and talking. Now let's talk about things breaking realistically. That's the domain of the physics engine.
Physics engines handle collision, rigid body dynamics, and joint constraints, the foundational math that makes digital worlds behave predictably. We have the native solutions and the commercial giants.
For Unreal, it's chaos.
Unreal Chaos Physics is Unreal's native system, and it is built specifically for high-fidelity destruction and real-time fracture simulation. It's what you see when a building breaks down into thousands of pieces cinematically.
And the middleware giants, the ones you can plug into any engine.
NVIDIA Physics is widely used, celebrated for its rigid body and cloth simulation capabilities, and is often GPU accelerated. But the truly commercial-grade option, favored by enterprise and massive AAA studios, is Havok.
Why is Havok considered so essential in the commercial sphere?
Havok is favored for its exceptional stability and deterministic performance at scale. In massive, networked open worlds, ensuring that every player sees the same destruction or physics result at the exact same time is crucial for synchronization. Havok has a reputation for reliability in multi-threaded computations. It's often chosen when stability and predictability trump raw visual flash.
And for 2D games, we see a completely different champion, right?
Absolutely. If you're building a 2D side-scroller or platformer, you don't want the overhead of a complex 3D engine. Box 2D is the gold standard for 2D games. It's lightweight, efficient, and most importantly, deterministic. That determinism ensures that the game state remains identical across all connected users, which is vital for smooth, reliable 2D multiplayer networking.
Finally, let's wrap this section with interactive sound. Most listeners don't realize the complexity required to make that single footstep sound correct as you move from a carpeted room to a wooden floor.
And that complexity is managed by audio middleware, like WeWise and FMOD. Crucially, as you said, these are not DA's digital audio workstations, which are used for composing. They are specialized software packages that abstract complex sound systems.
So the game engine just tells them what's happening.
The game engine talks to them by calling events like play footstep, and the middleware determines the correct sound file, pitch, volume, and processing based on the character's speed, the material, and the room acoustics.
Can you elaborate on the difference between FMOD and WeWise? They're the two champions here.
FMOD is often described as being more DAW-like and intuitive, making it generally easier to learn for composers or sound designers who are transitioning into game audio. It's very well suited for small to mid-scale projects because of its straightforward, event-driven workflow.
And what makes WeWise the choice for the massive, heavy projects?
WheelWise is generally considered more powerful, versatile, and technical. It excels at managing complex mixing hierarchies and integrating sophisticated randomization layers. For a massive open world, you don't want the same gunshot or footstep sound playing repeatedly. WheelWise makes it easier to set up complex, randomized systems that ensure unique sonic experiences, making it preferred for very large projects where organization and scale are paramount.
So we've created this hyper-real, intelligent, and dynamic world. Now we have to ensure the player can actually run it without their hardware just melting down.
Right.
This brings us to segment 4, the need for speed graphics and cloud gaming. We're focusing on the cutting-edge tech that boosts performance and, in some cases, removes the hardware barrier entirely.
The biggest performance revelation in the last few years hasn't been new silicon. It's been smart software optimization, specifically upscaling.
Let's define upscaling again for the commuter, just to make sure we're all on the same page.
Upscaling is basically a trick. We render the game at a lower, less graphically demanding resolution, say 1440p, and then use sophisticated AI or algorithms to intelligently reconstruct the image back up to a higher native resolution like 4K.
And the result is a huge jump in frames per second.
A massive performance gain, while preserving most of the visual fidelity. This has ignited the massive upscaling showdown between NVIDIA's DLSS and AMD's FSR.
Who holds the quality crown right now, particularly with the latest generations, DLSS 4 and FSR 4?
DLSS 4 NVIDIA is still the clear quality and speed leader. DLSS uses dedicated tensor cores on NVIDIA RTX cards, which gives it a massive AI processing advantage.
A hardware advantage.
Exactly. Sources suggest that DLSS quality mode preserves approximately 70% more detail in the image than FSR did in earlier comparative testing. DLSS 4 delivers noticeably better image quality, particularly in fine details and in motion, and it often manages to offer a small, maybe 5% edge in raw frame rate on top of that quality lead.
And DLSS's frame generation technology adds another layer of magic, right?
It does. Frame generation uses the AI to create entirely new synthetic frames that sit between the frames rendered by the graphics card, which dramatically increases perceived smoothness and maximizes visual fluidity without requiring the GPU to render that entire frame.
Okay, now let's talk about FSR 4, AMD's impressive competitor.
FSR 4 AMD is the open source approach, and it shows remarkable improvement over its predecessors. It is noted in our sources as being very impressive at 1440p. FSR doesn't require dedicated AI hardware. It uses general shaders, which is its primary advantage. Maximum accessibility and compatibility.
So FSR works on almost any modern graphics card, including older NVIDIA GTX models.
Precisely. If you own an older or non-NVIDIA card, FSR 4 is your best option for a massive performance boost. While DLSS holds the crown for absolute quality, FSR 4 democratizes upscaling by bringing substantial performance gains to a huge installed base of users.
That solves the software problem, but what about the technology that removes the hardware problem entirely? The Graphics Delivery Network, or GDN. This is the core technology powering NVIDIA's cloud magic.
GDN represents the end of friction and potentially the end of the traditional download. Traditionally, even with cloud gaming, you still had to own the game, download updates, and possibly have separate launchers.
Right.
The GDN platform removes two critical friction points: the need for the user to own the game and the need to install it. It fundamentally shifts the monetization model from selling a game to selling instant access and discovery.
So what does a one-click play experience actually look like for the commuter?
The use cases are revolutionizing discovery and consumption. Take the Metallica, Fuel, Fire, Fury Fortnite concert. Epic Games streamed the entirely interactive event directly to mobile browsers, Safari or Chrome, with just one click.
So you didn't need the app.
Users didn't need to install the massive Fortnite app, and they didn't need a dedicated cloud gaming subscription. They clicked a link and instantly joined the concert on their touch-enabled phone.
That is the ultimate frictionless experience, just instant engagement.
Another fantastic example is Ludeo, which leverages GDN for game discovery. They allow players to access and play bite-sized game highlights directly from social media links. Imagine scrolling through TikTok, seeing a clip of an intense moment in a game. You click the link, and you are instantly dropped into that exact moment to play it yourself for a few minutes.
So it's not a video, you're actually playing.
You are playing. This is instant access to interactive content, not just video. The power required for that low-latency streaming of fully interactive 3D content must be astronomical. What is the infrastructure behind this network? The backbone of GDN is housed in over 30 strategically placed data centers globally, utilizing incredibly powerful servers equipped with the NVIDIA All-40 series GPUs, which are based on the Ada Lovelace architecture.
And what does that mean in terms of performance?
It means these servers ensure that the consumer product, GeForce NOW, is capable of streaming the absolute highest quality, 4K resolution at 240 FPS.
4K at 240 frames streamed over the internet. I mean, that's a performance level that only the most expensive, dedicated local gaming PCs can even achieve.
And it's delivered globally with a near-native experience, even optimized for low-bandwidth environments as low as 5 millips per user. This democratization of high-end PC gaming is what GDN is all about. And this technology is not standing still. It is already preparing for the next hardware wave.
Which is streaming to extended reality headsets.
Absolutely. The GDN infrastructure is actively being prepared to stream to the newest extended reality XR hardware, specifically noting future Unreal and Unity applications being streamed directly to devices like the Apple Vision Pro.
Speaking of that next hardware wave, that takes us directly into our final segment, Segment 5, the next frontier extended reality XR. The focus of computing is rapidly shifting to spatial environments, and we are seeing a major platform battle brewing right now in 2025-2026.
The XR space has really become a complex triangulation, with developers navigating three major contenders, all trying to define what spatial computing actually means.
First up, the high-fidelity entrance from the company known for premium experiences, Apple.
That's the Apple Vision Pro, running Vision OS. This platform is explicitly focused on high-fidelity AR, or mixed reality, targeting the high-end consumer and the enterprise market. Developers build highly customized, premium experiences using its native integration with SwiftUI for the interface and RealityKit for rendering the 3D content.
So this is for visualization training.
We see it used heavily in visualization, enterprise training, and high-quality collaborative spaces, leveraging the device's stunning display quality.
Then we have the incumbent king of the standalone headset, Meta.
Meta Quest runs on Horizon OS. And Meta is actively rebranding its focus to mixed reality, or MR, to align with the market shift toward combining the digital and physical worlds. They're moving beyond pure virtual reality.
And they still own the volume market.
They dominate it. The Quest line is still known for accessibility, gaming, and social XR, covering a whole spectrum of devices from their Ray-Ban smart glasses up to the powerful Quest 3 headsets.
And the third major contender, gaining ground quickly due to its openness and integration capabilities.
That is Android XR. It is noted for its ecosystem integration and its sheer potential for deep AI-driven capabilities. Because it ties into the broader Android and Google ecosystem, we are already seeing some very advanced use cases being explored.
What does AI-driven capability mean in a spatial environment? What does that look like?
We're talking about enterprise applications for spatial AI navigation, using large models like Gemini, for instance, an AI that guides a worker through a complex warehouse task by digitally overlaying instructions in real time. Or AI-curated immersive video content via deep YouTube XR integration. Android XR's openness makes it fertile ground for rapid AI development and spatial computing.
This sounds like a developer's worst nightmare, though. 3 separate major platforms, potentially 3 separate software development kits, 3 different code bases to maintain. How does the industry prevent massive platform fragmentation?
That fragmentation problem was recognized years ago, and the industry's standardization solution is absolutely crucial for the future of XR, OpenXR.
OpenXR.
It is a royalty-free open standard developed by the Kronos Group. The entire goal is to provide a single, cross-platform API a standardized set of instructions for XR application development.
So instead of writing specialized code for Meta, specialized code for Apple, and specialized code for Android XR, they write one set of code.
That's the ambition. The chair of the OpenXR working group noted that where developers previously had to develop separate proprietary code paths for each headset, OpenXR gives them the freedom to develop once and quickly retarget to many different devices.
And everyone's on board.
All the major players, Meta, Sony, Apple, Valve, PICO, HTC, NVIDIA, they've all either adopted the standard or are actively integrating it. It's truly a unified push.
What's the latest critical update on this standard?
The Kronos Group recently released OpenXR 1.1. This release is highly significant because it focuses on consolidating multiple optional extensions into the core specification.
Why does that matter?
It drastically simplifies the development of advanced XR applications by reducing the variability and fragmentation that still existed between implementations. For example, it makes it far easier for Unity developers to use OpenXR for enhanced compatibility across various brands of hardware. OpenXR is the critical piece of plumbing required for the XR market to move forward and achieve mass adoption.
We have covered so much ground today, ranging from 3D modeling in 20 seconds to streaming 4K 240 FPS games to a mobile phone. Let's try to summarize the essential takeaways for you, the commuter listening on the go.
Start with automation. Generative AI is no longer a niche tool. Tools like Magic 3D are building production-ready models in under 30 seconds, and that insane speed is driving the market toward a $43 billion valuation by 2025. This is a massive shift in investment priority toward automated asset creation.
Then, the engine core. C++ still controls AAA performance because its manual memory management allows developers to optimize the frame rate down to the millisecond. But C#, bolstered by its TIOBE Language of the Year status, is winning the war of rapid development and platform accessibility thanks to safe, automatic memory management and its integration into the Unity ecosystem.
And the intelligence of the world itself is undergoing a revolution. Developers are moving past simple behavior trees toward powerful hybrid systems like GOBT, balancing intuition with dynamic planning and utility scoring. This new logic is complemented by conversational AI like NVIDIA ACE, which is powering NPCs to talk naturally and learn from players, running efficiently via NVGI optimization plugins.
And finally, the delivery. Performance is increasingly solved by software. DLSS4 remains the quality and speed leader thanks to its specialized AI hardware, but FSR4 is catching up impressively, especially at 1440p, while offering universal compatibility across all graphics cards. And the ultimate friction remover is the Graphics Delivery Network GDN, which enables one-click play of high-fidelity games, like that Metallica concert, streamed to up to 4K resolution and 240 FPS without requiring a single download or account installation.
The sources collectively point toward a future of unprecedented fidelity. We're talking about technologies that will make 8K resolution at 120 FPS the standard, a milestone that could be achieved with the next generation of hardware, like the RTX 6090 and Zen 6-based CPUs, coupled with future engine releases like Unreal Engine 6 around 2027.
But I think the real revelation and the most provocative thought we should leave you with isn't just graphical fidelity, it's conversational fidelity.
Indeed. With tools like NVIDIA ACE allowing game characters to speak naturally, understand complex context, and continuously learn from player tactics, the question changes completely. It's no longer about whether your virtual world looks realistic.
It's whether your virtual characters are realistic. What will it truly feel like when you can literally ask an MTC anything you want, and they respond intelligently, intentionally, and uniquely every single time? That is a level of personal immersion we have never experienced, and the underlying technology is arriving faster than almost any other trend in development.
A lot to think about on your commute today.